So this is the portion of the course where I remind you how extremely important units are. And so units will be necessary in every calculation that we do, and including them in all of the calculations within the work will be one of the ways that you can ensure that you are on the right track and that you end up with an answer that has the right magnitude. And I mean, sometimes even that you have the correct numerical value, that you've used the right conversion factor and whatnot. So units are important. Units are important because they give meaning to numbers. And exactly what this this meme is showing you is that without the context of a unit, you have no idea if your answer is really big or small or relevant or irrelevant. So we have to have units on the numbers that we are looking at. So there are two common systems. There is the English system and the international system. And the international system we abbreviate SI. And so this abbreviation, depending on the science classes that you've done before, you're probably familiar with it. So SI units are the standard units that scientists stick to worldwide. So we will primarily be using SI units. What is really wonderful about SI units is that they always have a base, and then depending on what we need, they'll have a prefix. And you can pair these up in any way possible, and the prefixes have regular intervals between them, which makes converting between them a lot easier than it is with some of the English units. So SI units, as I just said, have a base. And so that's what's being shown in this table here. So if we want to talk about length, the unit that we're basing this on is a meter. If we want to talk about mass, the unit we're basing this on is a kilogram, which is actually, it has this other piece in it, which is the prefix. So it just so happens that we use a kilogram rather than a gram as the base in the SI system because a gram is really, really small. If you think about the size and weight of an M&M is usually like piece of candy is what we usually kind of gauge our mental reference for what a gram would look and feel like. So as I said, the second piece is the prefix, and the prefix tells us the how big. So I said that a gram was really, really small. Let me find my reference in here. So on my table, if you take a look, and this is all, the factors are all in scientific notation. So if you have questions or concerns about scientific notation, you should let me know and I can recommend some practice problems. But we're starting 10 to the minus 15 is at the top. That's a really, really small. And then as we go down the table, we're going to 10 to the 12th, which is really, really large. In between, now these are randomly spaced, but we don't have every single prefix in this table. But in between prefixes, if we have them all, is a factor of 10. So you would multiply or divide by 10 to get between each of them. And in these, you can look at the factors of 10 to see how many there are between each. So my base unit is not explicitly listed, but it would show up about here, the base units are all 10 to the 0. And so my kilogram, which is listed here with a factor of 10 to the third, that means that there are 1,000 grams in 1 kilogram. Or there's 1 times 10 to the minus third kilograms in 1 gram. We'll be able to use those relationships in whichever direction you personally feel comfortable with. I have no preference on how you use the conversion factor. Okay, so they have some examples in here, but you'll notice that for the kilo example, they've listed meter, but I was talking about kilograms. That's the beautiful thing about the international system, is that this prefix is kilo, and then you just pop that prefix onto whichever base unit you need to work with. So they were working with a length unit, so we could also work with kilometers, right? And there would be 1,000 meters in 1 kilometer. So all of these prefixes will come up as we're going through and looking at numbers of different magnitudes. All right, now there are a few units that don't show up specifically in this table, and we refer to these as derived units. It just means that there's some kind of combination of the SI unit bases. So, and these are things that you'll be familiar with. So something like speed in meters per second is a combination of that length unit and a time unit. But when we talk about speed, we need them together. Volume is a derived unit, right? Because you're talking about length times width times height. So we might talk about something like meters cubed for volume. And density, which we are going to use this example right away. Density is also a derived unit, right? It is mass over volume. So something like kilograms per meter cubed would be a density unit. That is a derived unit. So density, which we will use quite a bit actually as we go to do some example problems. Density is an intensive property, which just means that it doesn't depend on how much you have. So it is not dependent on the amount. So, for example, if you had a 2-gram sample of iron, and a 5-gram sample of iron, they have the same density because they have the same identity, right? It's just iron has some density, and it's that relationship between the mass and the volume. So obviously these samples have different masses, so they would have different volumes, but they would be the same in terms of the density. So, and then just so you have it, the opposite of an intensive property is an extensive property. So mass is an extensive property. So this is something that depends on the amount that you have. All right, so I'm going to do a practice with this. I know when you watch the video, the problem will already be here. I'm going to pause this right at the problem, and then we'll take a look at it. So our practice problem says you've been given a ring that is supposed to be platinum, but it doesn't feel heavy enough The ring has a mass of 3.15 grams and a volume of 0.233 cubic centimeters. Platinum has a density of 21.4 grams per cubic centimeter. Is the ring platinum? Okay, so our density units look a little bit different, right? We have a different mass unit, we have a different volume unit, but that's okay. What matters is that we have mass per unit volume. So these are valid density values that we can look at. In terms of a solution, there are a couple of ways that you could do this problem. So especially here at the beginning, I think it would be a good idea for us to look at both of them. So one thing that you could do, and this was kind of the first thing that I thought of, it might not be the first thing that you think of, we'll call it option A. You could calculate the density of the ring you have and compare. So we have a mass of our ring, we have a volume of the ring. If we set this up, we should get the density of our ring and we can compare it to the density of platinum. So for the ring that we have, the mass is 3.15 grams. The volume is 0.233 cubic centimeters. So if we plug this into the calculator, we get 13.52 grams per cubic centimeter. So this is not a match, right? The density of platinum is 21.4. The density of our ring is 13.52. So this ring is definitely not platinum. So a second way that you could do this, we know the volume of a ring. I mean, we also know the mass, but let's say if this ring with this volume was actually platinum, what would the mass be? So we could calculate the mass of a platinum ring and compare it to the mass of the ring that we have. So it just means that the unknown piece of information that we are looking for is in a slightly different spot. So the density of platinum is 21.4 grams per cubic centimeter. And the volume of our ring is 0.233 cubic centimeters. And we want to know what the mass of this ring would be if it were platinum. So you have to do some cross multiplication, right? So whatever our value is in grams, it's going to be equal to 21.4 grams per cubic centimeter times 0.233 cubic centimeters. And this is good because we can check that our units are going to cancel. And if this ring were platinum, it would weigh 4.99 grams, which means our ring is definitely not platinum, which is good. We needed to get the same answer in both ways of doing it. So this is compared to the 3.15 grams, so not platinum. Okay, so the reason that I've put two different ways of doing this problem is to begin emphasizing a point about problem solving that I have for this class, which is either one of these would be worth full credit on any quiz or exam or whatever kind of graded thing you have, as long as you've shown all of your work and what you've done is a valid way to do it. If you did solution A, and just solution A, right? I'm talking about one or the other. This is great. It's labeled, you have plenty of work, and you have a definitive answer. B, it looks very different, but this is a completely valid way to do the problem. Everything is labeled, and you have a definitive answer. So I don't care which way you do something. Your work doesn't have to look like mine, but it has to be there. It has to be clear. I have to be able to follow it in order to give you points, especially partial credit. and it has to be a valid way of doing the problem.